Professor Zhou to give a talk. The title is From Enumerative Geometry to Statistical Physics and Quantum Mechanics.
Okay. Thanks. It's a great pleasure to be given an opportunity to talk about something that I have had in mind for some time, but it's probably not quite well known. So first, this is my plan of my talk. So I will start with enumerative geometry, and then I will walk through why we need to do something, think about it, statistical physics, and also then we also need some ideas from quantum mechanics. And if time allows, I will also very briefly talk about some application and some thoughts from fractional quantum Hall effects. So before I start the talk, I want to make an apology. So everything I will talk about is actually rooted in algebraic geometry, but I will actually not talk about algebraic geometry, but instead I will take a long march through physics-inspired territories. Grothendieck's Descent Dongfang will play a central role in my talk. So the background is intersection numbers of tautological classes on moduli space of curves. So let me give a brief recall of what classical enumerative geometry is about. So classically, people ask something very geometrical problems, some counting problems. Here are some classical results. So how did people solve such problems? There's some tool called Hilbert calculus. So let's start with something called Grassmannian manifolds, and then from a modern point of view, Grassmannians can be regarded as some kind of moduli spaces of linear subspaces. And then the Grassmannians has some kind of a cell decomposition, and you can decompose them into cells indexed by some combinatorial objects called partitions of integers, using a certain flag, and then you can define them, and also you can take their closure and then form cycles, and then you can consider their intersections. And then there are classically there are some rules called the Gambelli's formula, Pieri's formula, and some rules that describe their relations. So they're sort of like a combinatorial thing. But it turns out that actually they even though they are very geometrical, they also have some kind of algebraic counterparts. The algebraic counterparts are the symmetric functions. So the Hilbert cells actually correspond to Schur functions, some kind of special symmetric functions. And the Gambelli's formula and Pieri's formula and the Littlewood Richardson rules are actually they have some algebraic counterparts. They're identities for these symmetric functions. So on the one side we have geometry, and on the other side there is this algebraic combinatorics. There's somehow that's some kind of mirror. And another connection is to the representation theory of symmetric groups. The Schur functions form a basis of the space of all symmetric functions, but there are other bases. So one of the important bases is called the Newton power functions, and you multiply a bunch of Newton power functions, you get Newton symmetric functions, also indexed by partitions. Then they also form a basis, and then you can consider their relationship. That they can be expressed in terms of certain coefficients, and these coefficients actually are all the character table. That all the characters of all symmetric groups. So the symmetric groups have irreducible representations indexed by partitions, and also their conjugate classes are also indexed by partitions, and then the matrix between this Newton and Schur are actually character table of all the symmetric groups. So we have another side of the story. You have a representation theory, And there is in the 1940s, in algebraic geometry or differential geometry, it's known that these supercycles are also related to the Chern classes. You have these tautological bundles, and you can look at their Chern classes. And these Chern classes correspond to certain special supercycles given by this Young diagrams, the horizontal diagram or vertical diagram. And also there is something called the universality. If you look at the tautological bundle on the Grassmannian, but you take all the union, you take the space, the dimension of the space to infinity, and then any vector bundle of rank k, then you can find a map up to homotopy, and then you pull back the tautological bundle, and then you can they're isomorphic. So the Grassmannians are sort of like a universal objects. Okay, so let me summarize some of these features. This classical enumerative geometry is concerned with cell decompositions indexed by partitions. Then this set up a relationship to the algebraic combinatorics of symmetric functions and also symmetric groups, the representation theory. And also there is some kind of a universality of such objects. The Grassmannian are sort of like a universal. So some of these features will reappear in modern image enumerative geometry. So what do I mean by modern image enumerative geometry? So I view the modern enumerative geometry as mathematicians' quantum field theory or string theory. So it is well known that the development of modern enumerative geometry, including Donaldson theory, sorry, there's missing a D here, Gromov-Witten theory based on moduli spaces of various geometric objects. They are inspired by theoretical physics, Yang-Mills theory or string theory. So my attitude is that quantum field theory or string theory is sort of like a physicist's algebraic topology or enumerative geometry. And I regard modern enumerative geometry as mathematicians' quantum field theory or string theory. So it's sort of like two sides, two group of people, two mentality, but maybe there's something to share. So I will talk about the connection to statistical physics. So it's well known that they're related to quantum field theory or string theory, but I will talk about something that is less well known, statistical physics or maybe quantum mechanics. Okay, so I will actually focus on Gromov-Witten theory. So I will not talk about how they are defined, how they are developed. It's a long history and complicated, so let's just make things short. Just say that Gromov-Witten invariants are, in general, very difficult to compute. So like in algebraic topology, you first define homology group and the homotopy group, but some of them are easy to compute, some of them are very difficult. So Gromov-Witten invariants are very difficult to compute, but sometimes we really want to compute them and to see something. So they can be computed in some special cases. For example, the Gromov-Witten invariance of a point or the projective line or some toric Calabi-Yau threefolds or orbifolds, and also Gromov-Witten theory of a quintic Calabi-Yau threefolds, and maybe some generalization. So the corresponding mathematical results are a Witten conjecture and Kontsevich theorem. That's for the Gromov-Witten of a point. And Gromov-Witten Who-its correspondence that changed Gromov-Witten invariance of projective line to some classical thing called Who-its numbers, which can be dealt with by representation theory of symmetric groups. And also a mathematical theory of a topological vertex, which converts the computation of toric Calabi-Yau threefolds again to some kind of combinatorial thing, which involves representation theory of Hecker algebras. And also mirror symmetry. Mirror symmetry is just say, for the quintic thing, let me just go to the next page. So I want to unify all four of these cases. It's relatively easy to find the common features of the first three cases. The first three cases all have matrix models. So I will talk about this a little bit later. And also they satisfy some kind of a quadratic recursion where Sorel constraints or cut and join equations, where Sorel constraints are infinite dimensional symmetries. cut and join equations are relatively simple. They also satisfy a system of infinitely many partial differential equations called integrable hierarchies. So KdV in the Witten-Kontsevich case, TODA in the P1 case, and multiple component Kp in the case of thoery Calabi-Yau threefolds. But in the quintic case, it's not known. But in the quintic case, or fourth case, my misspelling here. So the hallmarks of the mirror symmetry is this mysterious appearance of hypergeometric equation. So there is a quintic fifth order differential equation, partial ordinary differential equation. If you solve it, and then you somehow can express everything in terms of that equation alone. And physicists suggest something that they're guided by something called the special Kähler geometry, and from that they derive the so-called TT star equation or BCOV anomaly equation. So it is then natural to expect the appearance of the hypergeometric equation, the special Kähler geometry, also in the first three cases. So, so my dream is to unify everything, the Witten-Kontsevich and also the quintic Calabi-Yau. And then on one side you have hypergeometric equation, on the other side maybe they should appear again. And also a special Kähler geometry. In the setting of something very algebraic and combinatorial, like the Soro constraint or integrable hierarchy. So I call, eventually I will see how they appear. So I call that kind of thing emergent geometry. And the emergence is something that I borrow from statistical physics. So actually, we borrow other things also from statistical, the Landau-Gingzburg paradigm of phase transitions, Wilson's space of series, and renormalization, and so on. So everything, if it is not so familiar to geometers, they actually borrow from statistical physics. So let me recall some of the developments. So, you know, we want to study the moduli space of Riemann surfaces, let's say genus G Riemann surface with n mark points. And then actually, again, as in classical enumerative geometry, we want to somehow decompose this into cells. But this time it's decomposed into orbicels. So by studying the quadratic differentials in the previous talk, there is something called the Strabo differential, and then it's some result due to Harrell, Mumford, and Strabo, that there is a combinatorial model of the moduli space, but you have to multiply it by this, the length of the boundary, sort of like something like that. And then you have a combinatorial model that somehow decomposes its moduli space into some orbicels, some cells with some automorphism group. So the gamma here are some kind of like a ribbon graph. So we actually have seen the decomposition in the quadratic differential, and then you look at the vertices, and then using this horizontal trajectory, and then you can decompose this into the Riemann surface into some ribbon graph, and then you can start to do the counting. So, so the E gamma here is just the number of edges of the graph, and here you can look at the combinatorial object automorphism. So then the first famous result is the formula of Harrell and Zagier. So you look at the moduli space, and you have the cell decomposition. You want to look, the simplest topological invariance is the orbifold Euler characteristics. So you just say you take the cell and you look at its contribution is -1 to this, and then you divide it by the automorphism group of the graph. And then it's amazingly, Harrell and Zagier found a formula that somehow this kind of Euler characteristic is related to Riemann zeta function. So that they're given by the Bernoulli numbers. So they get all of them, and so first they compute the moduli space of genus 1 mark point, and using the relation between chi of mg and chi of gn minus 1, they get this formula. So amazingly, to do the counting, So it's a geometric problem, but it becomes a combinatorial problem. But somehow the combinatorics is very interesting. In their proof, they compute some kind of a integral on certain space of Hermitian matrices. So it's sort of like a Gaussian, and then they compute the moments of this Gaussian thing on a space of Hermitian matrices. And actually, matrix models seem like deus ex machina for modern enumerative geometry. They play a more and more important role, surprisingly. It was actually originated in mathematics with important contributions by two scholars from Tsinghua University here. So one of them is called Xu Baolu, and the other is Hua Luogen. So Xu Baolu in the 1950s and Hua Luogen in the 1950s. And strangely, in the 1950s, Wigner suggested to use the eigenvalue distribution of large random matrices to model the energy level of nuclei. It's a very strange proposal, but some people take it seriously and developed that in the 60s. Dyson and other people, and they discover something called orthogonal polynomials, and they apply this to the matrix model thing. And in 1970s, Dooft introduced the summation. He relates the matrix model thing to Feynman graphs, but not the ordinary graph, but the ribbon graphs. So it's before mathematicians studies these things. In 1980, this physicist introduced matrix model techniques to the enumeration of ribbon graphs using matrix models. Hara and Zaghe rediscovered this method. Penner actually, he somehow introduced a better model because he knew about this specific ejection-Zuber thing to directly compute all of them. And in the late 1980s, string theory started to use matrix models to study two-dimensional quantum gravity. So physicists always make interesting proposals. Sometimes when these proposals are proven to be incorrect, they propose the application to some other thing. So instead of using to study high energy nuclei resonance, they say this string series matrix model can be used to study two-dimensional quantum gravity. And then they discovered the connection to infinite-dimensional integrable hierarchies, such as the KDV hierarchy, KP hierarchy, Toda, and other things. And also infinite-dimensional symmetries, like a Virasoro constraint and W constraint. And there is another more geometrical approach proposed by Witten using his topological gravity, which was inspired by Donaldson theory. So Donaldson theory was somehow, Witten proposed something called the topological quantum field theory, and then we have topological everything. So nowadays we have also topological insulator, topological matter, and everything. Somehow they originated from Witten's topological quantum field theory and inspired by Donaldson theory. So it's a very beautiful story about interaction between mathematicians and physicists. So anyway, Witten showed that his topological gravity is related to the intersection numbers of psi classes on the Riemann-manifold compactification of Riemann surfaces. So on this moduli basis, we have something called the cotangent line bundles. We have n Mach points, and then we have n line bundles, and we can look at their first-term classes. And then we look at their intersection numbers on the moduli space, and we have to consider all of them. So then we run into big trouble. For me, for the first time, I got scared because there are infinitely many variables. I'm only used to deal with things with only finite many variables, but suddenly somehow there are infinitely many of them. And then we can conjecture that this is a tau function of infinitely many differential equations. So how is that possible to prove anything like this? Okay. And then there are also infinitely many symmetries, Virasoro constraint. So the TJs are the variables to keep track of everything, and then there are infinitely many of them, and then you can write down infinitely many such things. And then in physics literature, the KDV hierarchy was derived from matrix model by something called the double scaling limit. So the KDV thing also has a long history. It first was observed as some kind of a solitary wave in the water, but then it becomes mathematics, and there is a long history which I have no time to talk about. But anyway, Kontsevich used a different kind of matrix model without taking the double scaling limit. He used the combinatorial model for the moduli space, used the ribbon graph. Originally discovered using the quadratic differentials. And then he proved an identity called main identity relating the intersection numbers. There's a bracket here which is missing. He considered certain generating series of these intersection numbers and then rewrite it as a sum over the ribbon graphs. The details of this thing is not important, but it's just like on one side you have geometry, on the other side you have these ribbon graphs, summation over ribbon graphs. And then he converted that summation of ribbon graphs using matrix model techniques into some matrix model, which nowadays is called the Kontsevich model. And then starting from this, he proved that this thing satisfy the KDV hierarchy, and that is more or less standard in that setting. So let me just say what more. So Panner model and Kontsevich model are both involve summation over ribbon graphs, some fat graphs, not just the ordinary thin graphs. More generally, you can look at the Gaussian unitary ensemble. You look at certain integrals like this. It's a formal integral, and then there's certain definition of this as a formal power series. It again involves infinitely many coupling constants. And then it becomes a sum over ribbon graphs again. There's always an order of the automorphism group has to be taken care of. And then you also have to somehow, that's a very important trick called the Dup's coupling constant. You can use this, and then you get some way to handle something. And then actually, this can be written in terms of the characters of symmetric groups. So you have some way to somehow manipulate this, and then you can use this to rewrite everything into character sums. And then you can start to get some explicit expressions. So as in the classical enumerative geometry, there is a deep connection to representation theory. It suddenly appears. It's not so clear from the Kontsevich model or the Panner model, but from the GOE, it's clear. And then they also satisfy that there's some standard trick techniques in the literature that you can find. You can prove that we are sort of constrained. Also, they satisfy something called a KP hierarchy. K and P are two Soviet mathematicians. Okay. So more interestingly, in this case, you can treat the coupling constant as Newton symmetric functions. So Newton and symmetric functions appear again, and then you can express everything, the partition function, the matrix, the humongous matrix integral, as a summation over partitions, and there are certain coefficients. The coefficients actually can be understood as the Preker coefficients, Preker coordinates. So in the study of the Grassmannian, there is this Preker embedding, and then there's the Preker relations. But here, actually, we get infinitely many of them. So we get infinitely many Preker relations, and it turns out that the geometrical Preker relations are equivalent to the Hirota bilinear relations. This was an amazing discovery of Sato. So that on the one side, you have nonlinear differential equation. On the other side, you get algebraic geometry of Preker relations. So the Preker relations are something like this. there are infinite many of them. Okay, and then Sato somehow say that even though we're looking at an infinite set of partial differential equations, but their structure is actually very algebraic. It's more geometrical. You look at the so-called semi-infinite Grassmann. You look at certain very special Grassmann, but with infinite thing on both sides. So you get infinite many positive powers, half integers, and also you get infinite many negative half integers. And then what describes the partition function is just the so-called affine coordinates. If you know the affine coordinates, you know the solution. So starting from the matrix integral, you get a tau function, and then you get a bunch of the affine coordinates. And how does this come about? You can get the so-called Pricker embedding by taking wedge. So given any point in a Grassmannian, and you take a basis, and then you take the wedge. But this is the so-called semi-infinite wedge, a formal wedge. And then there's something called the boson fermion correspondence. And then they take some of these bases to the Schur functions. Okay, so forget about all this. Then there is actually an explicit formula. You can use the so-called Frobenius notation to write down this. You start with the affine coordinates, and then there's a explicit expression to write down everything. Okay, so I think the details are not so important, but actually then something very strange happens. That there are actually something very nice. If you look at the commentaries of Young diagrams, then there are certain things called the hook numbers and the contents. So every partition is given by some boxes, and the contents are something like that. And then you can also fill in the hook length. So this is 1, 2, 3, 4, 3, 1, 1, 2. So you can just see them by just write down the Young diagrams, and then you can write down the explicit solution. And the coefficients here is complicated, but it's fixable. Okay, and then let's go on to get more. And then ribbon graphs are just special cases of Grothendieck's Descent Danfang. So it is related to the branch covering of P1, but branch over 0, 1, and infinity. The ribbon graphs are just special Descent, which is just we call it clean Descent. So it just then you can also count the Descent by modular the order of the automorphism group. They always have something about the automorphism group that you have to take care of. And then you can define the so-called Descent partition function, and there's free energy. Just you get infinite many of them. You have to look at all of them and the sum of them. You get infinite many parameters, and then they also satisfy Virasoro constraint again. They are KP hierarchy tau function again. And then, strangely, if you express that into Schur functions and you look at the coefficients has a very simple and nice expression. Unexpected, but somehow it happens for these things. Okay, how is that proved? You use representation theory, and then you do summation, and then there is an amazing combinatorial formula that tells you that. And also, because we're looking at the Descents are ramified covering of P1 with only 3 ramification points, but you can look at more general Hurwitz numbers. And then you can do the same thing, do the same counting, then the Hurwitz number. And then again, you get something like a KP tau function. So all these counting problems give you a representation series thing, and also on the other side, you get KP tau function, and also you get something. And then for the Hurwitz number, it's related to moduli space of curves. There is some famous formula called the ELSV formula. Somehow, on the left-hand side is the Hurwitz number, which is combinatorial. On the right-hand side is more geometrical. You take some Hodge bundle and certain combination of Chern classes and also these side classes. And there's some very crazy thing in front of it, and then there you go. So the crazy geometrical thing becomes a simple combinatorial thing. And then there are some generalizations which makes this geometrical thing more complicated. And then again there's some combinatorial thing which makes it simple, and then you can prove some formula which is explicit nice expression. So again, these things give us a Kp tau function, and then there are many generalizations. So whatever you do this kind of a thing containing, you always end up with some kind of an integrable hierarchy, the Kp hierarchy or thoda or whatever. So it's a universal thing. Okay, so let me summarize this thing. Modern enumerative algebra produce infinitely many partition functions from enumerative problems, each with infinitely many parameters. We need to put them all together and study their relationships, such as mirror symmetry, or what physicists like to call duality. When I say duality, it means two things are somehow identical, but actually there are infinitely many of them. So statistical physics is a branch in physics that dealing with systems with very large degrees of freedom. They actually comes to rescue. So surprisingly, one-dimensional quantum mechanical systems also naturally appear. That's a big surprise. Okay, so let's put them all together. The Kp tau functions, Gromov-Witten invariance of a point of P1, and ribbon graphs, that sounds, and also Witten's R-spin intersection numbers, which generalize the Witten conjecture. And then there's also BGW theory and generalized BGW theory, and also there are some other things. And also in the physics literature, that there are infinitely many so-called PQ minimal models coupled with gravity, and they all come as Kp tau functions. So this is very universal. So how to compute them? Actually, I have a formula that somehow compute all this free energy or endpoint correlation function from the affine coordinates. To understand a Kp tau function is to understand the affine coordinates. And here is my formula, which is just say we can look at the generating series of the affine coordinates, and then we know how to compute everything. So if we know the affine coordinates, then we have a concrete way to compute everything. Okay, so how to find affine coordinates? So from enumerative geometry, we go to we get Kp tau functions, and then we need to find affine coordinates, and then we need to find the kernel function. So my formula actually is analogous to a formula in matrix model theory, which is they use the Christoffel double symbol kernel. So to understand the kernel in my formula, actually I need to borrow ideas from statistical physics or quantum mechanics. So let's just go to that. Because I think most of the people in the audience are not expert. Actually, I'm not an expert on statistical physics either. But let me just say what I understand, what I like about statistical physics. You have a very large degree of freedom, but you look at only finite many things, finite quantities called order parameters. You somehow cleverly find them. You denote them by phi 1 and phi n. And Landau and Gingzburg says that there's some function, the Landau-Gingzburg potential, that somehow, if you know this potential, you know the system. There's a very interesting story about Landau in the prison, and then he was helped by his friend, one of his friends, to get out of the prison to explain certain amazing physical phenomenon, and then his solution is this. It's something called the Landau-Gingzburg the critical mean field theory. Then you look at the critical point of this Landau-Gingzburg potential, and then you can understand phase transition. And then there's a famous paper by Anderson called More is Different. when you have a large degree of freedom, it's different. So Wilson is also, all these people are actually Nobel Prize winners in physics. He said we should look at infinite dimensional space of series. Each series is just a point in this space, but we have look at all the coupling constant. And on this space, there are some kind of dynamics. You're starting from a series with a given set of coupling constant. There are certain dynamics called the renormalization process, modify to get a new set of coupling constant. And then there are certain fixed points. They are correspond to so-called universality class. And also because you have infinitely many things, the collective behavior somehow is maybe surprising. It's called emergence. Okay. So now here we actually have infinitely many parameters. So we can look at the space called the space of Witten-Kontsevich, called the big phase space, with all the possible coupling constants. And there is also a small phase space, which we can take only the zeroth one. And you take the order parameter to be the derivative, the second derivative of the free energy in genus 0 with respect to T0. And it's an amazing thing discovered by Digraph and Witten using topological quantum field theory thing, that you actually get an equation. And this equation can be understood as just say, looking for a critical point. You look at the Landau-Gingzburg potential of this, and then you look at this critical point, that gives you that Landau-Gingzburg equation. And then you can renormalize this Landau-Gingzburg potential by shift the origin to another point, and then you get a bunch of coefficients. And the coefficients are just defined by, introduced by Jackson and Zuber, and the interpretation in terms of renormalization was due to myself. And then you can express everything somehow into, starting from a genus bigger than equal to 2 becomes a finite expression. So originally you get infinitely many things, but if you change into the renormalized coupling constant, so because of the degree constraint, it becomes a finite sum here. Even though here it's not finite, but it's more or less traceable. So for example, in genus 2, you only get 3 terms. And in genus 3, you get this many terms, but from infinite to finite. So there's a magic of renormalization that goes from infinite to finite. And if you look at the correlation functions, again, they become finite. So the whole point is that from infinite to finite by renormalization. And then you can use this to study the so-called phase transition, and you can go to different models. You start with the Witten-Kontsevich model, which is algebraic geometry, and then you change the parameters, and you go to other models, which is not algebraic geometry anymore, which is something like a Yang-Lee edge singularity, and that is physical. So that means somehow algebraic geometry can tell you something about physics. So on this side, it's just purely algebraic geometry. On this side, just purely statistical physics. And also, there are some other things which is related. Miyazakani's thing. If you look at Weil-Peterson volume, and the Weil-Peterson volume is related to W Witten-Kontsevich by just shift the variables. The coupling constant, you shift infinitely many of them starting from the T2. You don't shift the T1 and T0. So then my question I ask myself is, what about T0 and T1? What about shift there? You can consider all the possible shifts. The shifts are given by the higher Weil-Peterson volume. You just take the shift, and that's the result due to Manning and Zograff and Liu and Xu. So you take all these intersection numbers, they're related, they're going back to the Witten-Kontsevich. So Witten-Kontsevich is just a universal thing that somehow you shift this and you get all the other things, but not the T0 and T1. And what about that thing? So in the physical background is that in physics literature, there's some SYK thing and JT, and they make this very popular. And it turns out the geometry is Weil-Peterson volume. Okay, and then there's also this super gravity and super volume. And then it becomes, again, very geometrical. It becomes intersection numbers on the modular space again, but you have to use something called the theta class introduced by Nobbery. So Nobbery originally he used some other things to introduce the theta class, but it turns out to be possible to explain the supergravity about Stanford-Witten. Yes, and then there is something called that related to the BGW theory, and that's discovered in the 1980s, and they somehow many things come together. Okay, let me just say. Then the more recent thing is something called Anna-Arndt topological recursion. Something very surprising appeared again. So we can encode the information about the Witten conservage tau function into a simple algebraic curve, a plane curve. It's just a curve like this. You can prove that. But for the Weyl-Peterson volume, it's similar curve, but you have to modify the curve. And for the higher Weyl-Peterson volume, they're all somehow encoded in some curve, plane algebraic curve. And then on the other side, for the supergravity, it's very interesting that you just change z to 1 over z, and then you modify this curve, and then so for these things with infinite degree of freedom, you get something somehow everything is encoded into something very simple, and I call these things emergent geometry. Somehow something emerge. So because my time is running up, so I have to rush. There are many things about all different models, and then they somehow all have the same feature. And then they all somehow are described by certain topological recursion. So on the Witten conservage side, and also on the BGW side. The only difference is the introduction of z and 1 over z. Okay, so there are actually many more examples of topological recursion. So for the Hurwitz numbers, or for the Gromov-Witten theory of P1 and a topological vertex, thoery Calabi-Yau threefolds, or orbifolds, they all satisfy the topological recursion. So these are very common and universal thing. They also theoretically they are somehow under some conditions equivalent to the given tau formalism, and then I think these are important. Topological recursion is equivalent to intersection numbers on moduli spaces, and mathematical proof. Some of the mathematical proofs are given by myself. Okay, so why do they appear? I explained them as some kind of an emergent phenomenon. So here is one more recent result. So about the shift in T0 and T1. So its topological recursion somehow is also unified with this renormalization. So the IN and I0 appear in the renormalization. So this can be also used here to combine with the topological recursion. And let me just say that there are some other generalizations of this kind. But since my time is running out, let me just say I got infinite system, and then I got algebraic curves. But then where is this quantum mechanics? So I get many curves. So for all these enumerative problems, I encode information into some simple algebraic plane curves, and then there's many of them. So how do we put some order into this? How to somehow to see why they appear and how they are related? It turns out that we actually have to quantize this whole thing. We have to look at the quantum spectral curve. So using the topological recursion, you can also get the quantum curve, which is some kind of some differential equation like this. That's actually a Schrodinger equation. So from a Schrodinger equation, you quantize. In this case, you quantize this curve called the Airy curve, and then you quantize this. Then you get the Airy function and the Berry function, and then you can use this Airy function and the Berry function to describe the Witten conservage. Okay. So then what about the other things? So the quantization of spectral curves mentioned above, actually it turns out they produce hypergeometric equations. So like in mirror symmetry, hypergeometric equations appear. And then here is the diagram that we get actually a lot of these things. You get the Gauss hypergeometric function, and there are certain, according to Riemann, that you get these singularities, 3 singularities, and there are certain degenerations. The degeneration that gives you all sorts of like special functions. So everything somehow is unified in this picture. And then correspondingly, they correspond to this enumerative problems. So this is Witten-Kontsevich, this BGW, general BGW, and GOE and GULE, and everything somehow has a pattern. So they unify into this Gaussian thing. And also, why do we want quantum mechanics? You can look at the so-called wave function, the dual wave function, and use the after quantization, you find the wave function, the dual wave function, and then you can find the kernel. So everything somehow is just say you start with a system with infinite degree of freedom, but eventually everything becomes simple if you look at this more carefully. So let me just say some. I'm running a little bit over time, so let me just take 2 more minutes. So in statistical physics, there is some amazing thing called the fractional quantum Hall effects. And then in statistical physics, they have 3 kinds of most important statistics called Boltzmann-Gibbs, both Einstein and Fermi-Dirac. Fractional quantum Hall effect says that there should be more possibilities. Then there are actually some family of these things interpolating this classical statistics, but strangely, these things there is something mostly well-known things called Achaya-Suomi statistics. It actually corresponds to the Lagrange unitary ensemble, which is also related to Grothendieck's Glissant-d'Enfant. Okay, that's where it's surprising thing. I have a lot more to talk about, but have no time. Okay. So, thank you very much for listening.